Good morning, sir. It's me, Lawan Poudyal, along with my team members, Sijan, Swastik, Abhiyan, and Sushant. Today, we are going to explain ModSort, divide and conquer algorithm. Today's agenda are going to be introduction to ModSort, divide and conquer paradigm, the merge process, recurrence relation, complexity analysis, applications, advantages and disadvantages, at last but not the least, conclusions. Let's go through introduction. So, what is ModSort? A comparison-based sorting algorithm invented by John von Neumann at 1945. It uses divide and conquer strategy to sort lists or arrays. The main concept is it breaks down the problem into smaller parts, sorts them, and then merges them. Let's talk about divide and conquer. This algorithm first divides the unsorted array into two equal halves and then it conquers it. That is, recursively sorting the both halves. And then it combines it, that is, merge the two sorted halves to produce a fully sorted list. On a visual note, think of splitting a deck of cards and then merging it carefully. Now let me walk you through the merge process. First, it compares the first element of each array, that is the smallest arrays as the both arrays are sorted arrays, and then appends the smaller element into the new resulting array. Now it moves the pointer forward into the array from which the element was taken, and then the process is continued till one array is exhausted and then appending the remaining elements into the resulting array. By this way, we get a sorted array.
Hi, I'm Abhiyan Regmi and I'm responsible for explaining the algorithm and the visualization of merge sorting. Basically, the merge sorting, there are two parts of merge sorting, or to be precise, there are two functions that is responsible to complete a merge function, a merge sort algorithm, and that is merge sort function and merge function. Basically, we will be discussing about merge sort function first. The merge sort function basically is responsible to recursively divide the array or the vector into sub arrays or sub vectors in equal length for even situations, or for odd situations we'll be talking about them in the later portion of the slide. Now the other task of merge sort function is to send the left and the right sub array for sorting and then be brought back in ascending format. And one thing to be noted is that when merge function arise within merge sort function, we won't be discussing about how it's implemented right then, but after few slides. So let's just start how the merge sort function works. It actually takes three parameters. Basically, takes an array or a vector and leftmost and the rightmost index of the array or the vector. Basically, in our condition, the first array will have the leftmost index to be 0 and the rightmost index to be 7. That is the length of the array or the vector minus 1. And the first line that we see here actually checks if the length of the vector that we have provided is of 1 or not, because if it's of length 1, then there is no need to partition such array and it prematurely terminates. Basically, now this one actually calculates the the value of the mid index. The value of the index of the middle elements in this condition is actually 3, that is 772. And the merge sort function is recursively called again, which splits our array or vector into its leftmost part, and then it's recursively called again and again till an array of length 1 occurs. Basically, during this time, the first line, that is the if statement, becomes true and the function prematurely terminates. And now the line after merge sort array left mid, that is merge sort array mid plus 1 right, will occur. That will split the array into its rightmost sub array, which is also of length 1, so it also prematurely terminates. And now finally the merge function occurs, which basically sorts the given sub array or sub vector. So now its sorted form is 932 and 588. And now again the leftmost sub array of the given sub array in that particular call stack will be called and which are in our condition is displayed right here. And again, the leftmost part is of length 1, so it prematurely terminates because of the first line. And same thing happens with 772. And since these two elements in arrays are in this incorrect order, they look the same after being after being sorted. Now finally, the two sub arrays will be merged in such a manner that the least element of each of the sub array is first compared, and which of these and each of these element, once are checked to be smaller than the other one, will be stored in our actual array, so which in this condition is 93, and 5 comparing this, it would be 203. Comparing the rest of the two elements, it would be 588, and then 772 for, and then finally the rightmost sub array of our second call stack will be called, and due to and it will be sorted in the same manner. Now these two sub arrays will now be sorted in the manner that I previously explained. So 93 is smaller than 466, 203 is smaller than 466, 466 is smaller than 588, and will be sorted in the following manner. So finally we get our array. Now let's actually talk about how the merge function that I didn't explain previously actually works. It takes four parameters, three indexing parameter and an array basically. And the merge function, let's just take an example of a sub array that actually did occur in one of the examples that I mentioned before. So here the left index is 0, mid index is 1, rightmost index is 3. So n1 is the length of the rightmost sub array or sub vector, which is 2, and n2 is the same for the right sub array or vector. Right sub vector is what I was trying to say. And then let's just create two temporary sub array or sub vectors in such a manner, and then finally assign each of the consecutive values of our actual array into these sub arrays or sub vector. And finally, let's just initialize two I and j iterative variables with 0, and another k variable with the with the index of our left parameter. The while loop checks if I is more than n1, that is the length of the first sub array, and also checks if the second iterative variable is smaller than the length of the second sub array, which is our rightmost sub array or sub vector. And now it checks the first element of each of the sub vector, and if either one of them is smaller than the other one, that will get to be placed before the other one into our actual array, which in this condition would be 93, which here actually is true because 93 is smaller than 203. So this one 93 will be the instruction inside of the if block will be executed, and 93 will be placed inside of our actual array. The same will happen now. I will be incremented and k will be incremented, and now the iterative condition is checked, which is true, so the iteration continues, and now it's checked between 588 and 203, which basically right now will execute the else block statement because 588 is not smaller than 203. So 203 will be stored first, j will be incremented and k will be incremented obviously, and then the iterative condition is again checked, which again is true, so the iteration still continues. Now the checking is done between 588 and 772, basically resulting in a true condition for the if block. So the instruction inside the if block is executed, due to which 588 is placed inside our actual array, and then I is incremented as usual, and k is also incremented as usual. Now the iterative condition is checked, which yields a false value inside of the while statement. Therefore the iteration discontinues. And now these two while loops that we can see down below are basically to check if all the elements in the right or the left sub array have been inserted into our actual array or not, which for the right with left array is actually true. Therefore it yields a false value, and this iteration does not even continue at all. But the second iteration does continue because the j's value is smaller than the length of the rightmost rightmost sub array or sub vector, and assigns the last element into our vectors as it is, and then increments j and then increments k, basically resulting in a false statement for the iterative condition, and the iteration terminates, finally yielding a vector or an array that is in a sorted manner.
My name is Swastik Bhandari, and I'll be covering two topics today. One is the recurrence relation, and another is the time complexity of the merge sort. And recurrence relation can be helpful to find the time complexity of the algorithms which uses recursion. And here you can see the recurrence relation of the merge sort, and I'll be explaining this in detail in next slide. And here we can Okay, we perform merge sort using recursion by calling left half and right half. Yes, so I'll be representing the stack frames in the form of tree. This is the root, and this is left subtree. This is right subtree. And to find the total time complexity, if we know the time complexity of the left subtree, right subtree, and the root, we can sum up uh, all the time complexity to find the total time complexity. As you can see here in the recurrence relation, this is the time complexity taken by the root, and these two are the time complexity of the left subtree and the right subtree. If you consider the root node, the root of the left subtree, then we can further simplify this to Tn by 2 is equal to 2t n by 4 plus n by 2, as we have half of the current size. If we combine these two relation, we get 4t n by 4 plus 2n. Okay, if we continue this process, okay, how many times we have to perform this? Up to the height. Okay, because every time I am dividing into half, so when all the nodes, the size of the node is 1, we have to stop. So we can, in general, we can write the equation like this. Um, and we know the height, if we have n number of nodes, then height is log n. So we can replace that. And at last, we get Tn is equal to n plus n log n. The highest factor is n log n. So the overall time complexity of the algorithm come out to be n log n. Okay. And there is no case of early return. So worst case, best case, and the average case all come out to be n log n, as you can see here.
I'm Sijan Bhandari, and I'll be talking about the application of merge sort, which is external merge sorting. And it is a sorting process which is used when our data is too large to fit into our primary memory, and it relies on its external memory, text, using text for sorting. And it is carried out in two processes. One is the sorting phase, the other one is the merge phase. In the sorting phase, the chunks of data that is small enough to fit into main memory, they are read, sorted, and then they are written out to a temporary file. And in the second phase, the merge phase, these temporary files or the sub files, they are combined into a single larger file. So let's say we are given an input sequence of 9 elements, and say we have our primary memory which can only act upon three elements at a time. So how to perform the sorting of these elements? It's simple. We first start up by breaking this data into smaller chunks of three elements, which is small enough to fit into our primary memory. And we feed them into our primary memory. We perform internal sorting of our choice, and we write them back to the text in a temporary file let's call them run1. And this temporary files, they contain sorted elements, and these sorted elements, these are called runs. And similarly, carrying out for other three elements 6, 4, and 10, we write them into our RAM, we sort them, and we write them back to the text in a temporary file. Let's call it run2. And similarly, for other three elements 1, 7, 5, we write them back into the text in a temporary file run3. And for our final elements 3 and 1, we sort them and we write them back to the text in another and temporary file run4. And at the end of this splitting process, we end up with 4 runs: run1, run2, run3, and run4, which are sorted within themselves. And we begin our next step, which is the merging phase. We take two elements, and we take first two elements from each of these runs, and we put them into the input buffer of our run. And we compare between these two elements of the input buffer and write this output, which is the smallest number, into the output buffer. And this output of the output buffer is then written back to the text in a temporary file. Let's call it run5. And since 2 from run1 is placed in the run5, we bring in another element from run1, which is 8, and repeating the process again, comparing between two elements, we get the smallest element, which is 4, and we write them back to the text in the temporary file. And repeating the process again, we compare between 6 and 8, and we write the smallest one into or temporary file. And for 8 and 10, 8 goes into the temporary file, and for 9 and 10, 9 goes into the temporary file, and at the end, since 10 is the only element left, it is already sorted, and we have our temporary file, which is run files. And now we repeat this process again for run 3 and run 4, and we end up with run 6, which is a shorted run. And after the first merge pass, we end up with two runs, which are shorted within themselves. And the next step is quite simple. We repeat this process again. And after merge pass 2, we get our finally shorted run, which is the output sequence, and which is written back to the disk, and this is shorted. And to sum up all this, we first split the data into smaller runs, we sort those runs and merge them back together. And this allows us to efficiently sort massive outputs or massive amounts of data using external storage.
Right, today I'm going to discuss about the advantages of mod sort. One of the biggest advantages of mod sort is its predictable and consistent time complexity of n log. And unlike other sorting algorithm like quicksort, which can degrade to n square in worst case scenario, mod sort always maintain an efficient n log n performance no matter what the input is. This make it reliable for large dataset and ensure that sorting time remains reasonable even in worst case scenario. Another key benefit of mod sort is that it is a stable sorting algorithm. Stability means that if two elements have same value, their original order in the input list is resolved in sorted output. This particularly important in application where sorting is done on multiple attributes, such as sorting a list of students by their GPA. This feature makes mod sort for ideal for application that requires an consistency. Another advantages of the mod sort is efficient. It is efficient for large dataset. Mod sort is highly efficient when dealing with large dataset, especially when compared to algorithm like bubble sort or insertion sort, which has time complexity of n squared. The divide and conquer approach ensures that the large amount of data can be processed quickly and efficiently. This is why mod sort is often used in scenario where performance is critical, such as database sorting, large scale data processing. Let's discuss about another advantage, non-adaptive performance. One thing to note about the mod sort that it is non-adaptive, meaning it does not take advantages of already sorted data. Even if the input is partially or fully sorted, mod sort will still perform all the necessary steps to divide and merge the element, leading the same time complexity. While this guarantees a consistent performance, it also means that other adaptive algorithms like insertion sort might be faster for nearly sorted data. However, in case where performance predictability is more important, mod sort remains a strong choice. Let's discuss about the disadvantage of mod sort. One of the biggest disadvantages of the mod sort is its high space complexity. Like other in place of sorting algorithm like quicksort or insertion sort, mod sort requires an additional memory proportional to the input size. Specifically, it uses a space complexity of bigger notation and which requires extra space for temporary array during the merging process. This makes it least suitable for memory constrained environments such as embedded system or large scale sorting where memory usage is critical factor. Another disadvantage is insufficient for small datasets. Mod sort is highly efficient for large dataset, which we already discussed in the previous slide. But when it comes to a smaller input, it often outperformed by a simple algorithm like insertion sort or selection sort. The overhead of the recursion function calls and additional memory allocation makes mod sort slower and less efficient for smaller list. In practical scenario many hybrid sorting algorithms switch to insertion sort when dealing with small sub-array to optimize performance. So let's discuss about the another disadvantage, complex implementation. Another challenge with this is its complex implementation compared to simple algorithm like bubble sort. The recursive nature of mod sort requires a careful handling array in index, merging logic, and memory management. This makes it harder to implement correctly and debug, especially for beginners. While it is powerful algorithm, its complexity can draw or drawback in cases where simplicity is preferred.
Now, to conclude this, ModSort is a robust, reliable, and stable sorting algorithm. Its divide and conquer strategy provides predictable performance with big O notation and log and time complexity. It is widely used in scenarios where stability and consistent performance are more important than minimizing space. At last, on behalf of my team, I would like to thank you, sir, for providing us this wonderful opportunity. Thank you.